In this video, we're going to discuss vector addition. It's an operation that takes two vectors, adds them together to get a third vector. It's very easy to do when you're given the components of the vector. So the component form of vector addition is just to take my two vectors u and v, and the sum u plus v is obtained by summing up their corresponding components and getting a new vector. I've written it here in 3 dimensions, but I want to discuss geometrically what it means, and it's just easier to visualize that in 2 dimensions, and I've drawn my 2 vectors below. So what does vector addition look like geometrically? And this is far more important that you leave the video understanding how to interpret it graphically. Here I have my vector u and I have my vector v, and I've chosen to draw them beginning at the same point. Remember, I can draw a vector wherever I want as long as I have the same direction and magnitude, and I'm just choosing to start here at the same point. Now, what does it mean to add the components together? The first component would be u1 plus v1. Well, u1 is telling you how far you displace to the right in this case, according to u, and then v has some rightward displacement as well. That amount there is v1, but I'm going to make that a cumulative thing by tacking it on to my current displacement. So I go u1 and then I add v1. And then I do the same thing. u2 will tell me how far to displace up according to u, and then v2 gets kind of this vertical displacement here gets added on to that. And well, my vector then, my sum vector, is going to go from here up to this point here, starting at that same point. And the way to visualize that is to draw a parallelogram. So I'm going to take my vector u and I'm just going to draw the same line or the same arrow parallel to it in a different location. So that's actually the same vector there, u. And then I do the same thing here, v. I move that across parallel. So that's v there as well. And then I'm just going to draw the vector that begins at that same point and ends at that corner of that parallelogram that they form. And that's going to be the sum of the two vectors. So this principle is called the parallelogram law, and it says that u plus v is the diagonal of the parallelogram formed by the vectors u and v. In 3 dimensions, that same principle is true. Just imagine 2 at least non-zero vectors, and they will form a parallelogram if they're not parallel to one another, and then you just kind of do the diagonal of that parallelogram to get the sum. Okay, so let's look at vector subtraction, because vector subtraction u minus v is really just a form of addition. It's u plus the opposite of v. So I'm doing scalar multiplication first and then adding the vectors together. So that tells us how to actually do this graphically here, or rather in terms of components. The first thing I do is I just subtract the corresponding components. And of course, the order I do that in matters. So it's u minus v, so u1 minus v1, etc. for the components. But graphically, what's this look like? So here's my picture again. Here's u, here's v. And the first thing I've got to do is scale v by a factor of -1. So that means to take the opposite vector minus v, pointing in the opposite direction, the same length. And then we're going to add those two vectors together. And to do that, we'll use the parallelogram law to do that. So I'm going to draw the parallelogram that minus v and u form. And I'm going to draw the diagonal formed by those. So that there is the vector u minus v, starting at that point there and going to the corner of the parallelogram. Now, it was a little awkward that I first had to find minus v and then apply the parallelogram law. But remember, you can draw a vector wherever you want as long as you have the same length and direction. And it's customary to just kind of move that up parallel so it starts at the tip of v and ends at the tip of u. And so, here's kind of the same picture, but without the extra noise. The difference, u minus v, starts at the tip of v and ends at the tip of u. And it really is, if this vector is kind of telling you you start here and this vector says you end here, then u minus v should be the displacement. So it's pointing towards the end point. So the principle is u minus v is formed from the tip of v to the tip of u. If I subtract in the opposite order, if I go v minus u, then I'll get the vector pointing in the opposite direction. It will start at the tip of u and end at the tip of v, because it's like a displacement. It's saying end is v, start is u, and you're displacing from between those 2 points. Let's look at an example. I'm going to let u be the vector 1, 2, and I'm going to let v be the vector minus 2, 3. And let's find the length of 2 times u minus v, and we'll interpret it graphically as well. So we just work in terms of components and do those operations, and at the end we'll find the length. So let's find that vector first, 2u minus v. I'm going to double the components of u, so 2 and 4. And then I'm going to subtract the vector minus 2 and 3, the vector v. And that just means to subtract corresponding components. So I'll have 2 plus 2, 4 minus 3. And that will get me 4 and 1. So the difference of twice u and v is 4, 1. We can find its length now. We sum up the squares. 16 plus 1, square root of that gets me square root of 17. Let's think about this graphically. I'll make an attempt to plot these relatively reasonably. So u is the vector 1, 2. So I go 1 over and 2 up. And then v is the vector, or I'm sorry, then I'm going to double it first. So I'm going to make it twice as long. So there's 2 times u. The components of that will be 2 and 4 as a result. And then v is the vector minus 2, 3. So I go over 2 and 3 up. And the difference of those, so 2u minus v, is going to be starting at v and ending at 2u, because its displacement is kind of like end minus start. So we end here and we started over here. And the length of that blue vector then, 2u minus v, that length there is square root of 17 units.